Okay, so this talk is going to be all about QBasic. I'm just kidding, that's a joke. So I'm Gal, and I'm going to be talking about recommendations meet web browsing. Can you hear me? Just talk on this. And this is joint work with Roy Ronen and Elad Yom Tov at Microsoft here in Israel. I will say there's also a paper that details most of the ideas here, which I'll refer to during the talk. So if you're interested in more details that I don't get into, you can check that out. I can give you a link if you're interested. So let's get to it. Thank you for having me. So with respect to the previous speaker, I'm going to offer a little bit more motivation for you guys, especially those who just came into the room. So let me just motivate by saying, Okay. So let me just start by saying recommendation systems are everywhere. And these days, maybe you don't know it, but they're all around you, and I'm going to give you just a few examples. So, of course, the Microsoft Windows Phone has games and apps that are picked just for you. Amazon.com has recommendations based on the item you're currently browsing, in this case, your book. Google, of course, has games that are recommended just for you. The famous Netflix front page has movies and TV shows that are fixed just for your personal pleasure. The Microsoft Windows Store has Windows apps and Windows games. Match.com uses personalized recommendations just for dating. Goodreads.com has personalized recommendations. Interestingly here, we have an explanation. Huffington Post has suggested for you news articles. eBay.com has item recommendations based on the item you're currently browsing that you may also be interested in. And a local example, RamiLevy.com.co.il has some pita recommendations for you in case you're interested in pitas. So I hope I've shown you that recommendations are everywhere. And I'd like to go through a small survey of the main approaches that are used in industrial applications to power these types of scenarios, right? So that's not to say these are the only approaches that are possible for recommendations, but in many of the industry systems, we'll see these over and over and over again. Okay, so one family is the content-based family. Essentially, I take each item in my catalog and I map it to a machine-understandable format, in this case, a vector of numbers. Numbers are sometimes called features in this context. And then this allows me to compute a similarity between every, that's not supposed to be like that. So this allows me to compute a similarity between these two games, which is what's supposed to be in that. So at query time, when I'm using a content-based approach, query time is the time when user X requests a recommendation from my recommendation system. I use my similarity function to compute those items that are very similar in that sense to those items installed by user X, and I recommend those items to them. This has a great advantage in that explanations are super easy. I can say, I recommended Harry Potter 2 to you because you watched Harry Potter 1. So that's a great advantage, and many of the requirements in recommendation system involve explanations. One problem with these approaches, well, they depend a lot on the actual features that I choose. For example, in the movie domain, I might say whether the movie is a horror movie or a documentary, whether it's directed by Steven Spielberg or George Lucas, what's its IMDb rating, what's its Rotten Tomatoes, is it made in the 40s or the 50s, and so on. And you can see that these kind of design choices will not translate when I'm doing apps and books and so forth. And so in order to make these kind of systems work, the recommendation system engineer has to be well-versed in the content domain of the item catalog. And thus, it precludes using the same approach across different domains. So another family of approaches is called collaborative filtering. And here we represent each user in our data as a little basket of the items they've consumed. So here user 1 is represented as these 3 movies, and user 2 is represented as another set of 3 movies. I don't know if you can see, but there's an overlap. And this allows me to compute a similarity between these 2 users. So at query time, user X requests a recommendation. I simply find all those users in my system that are similar to user X according to my similarity function. And I recommend those items that those users installed. So one great advantage to this, which sort of addresses the previous concern is that we're using only so-called usage signals. That is, only those interactions between the user and the catalog items, right? So I don't need to know what the domain is, if it's movies or books or whatever. I just need to know who bought what or who rated what and so on. One disadvantage to this sort of approach is consider 3 users. User A watched Harry Potter 1, user B watched Harry Potter 2, and user C watched Back to the Future 2, say. If we're using this sort of Jacquard basket similarity, all 3 users will have a distance of 0, or a similarity of 0, rather. And this is obviously undesirable because obviously the user who installed or watched Harry Potter 1 and 2 have something in common. So a subset of collaborative filtering approaches called matrix factorization sort of works to remedy this. Now, matrix factorization works by first abstracting your data into this sort of matrix representation. And here the rows are indexed by our users of our system, and the columns are indexed by the items in our system, in our item catalog. So an element that has a 5 in, will this work for me? So this user rated this movie a 5, and this user liked it less, so he rated it a 1. And this is sort of the conceptual underpinnings of this matrix factorization approach. The problem is, in most industrial applications, we have the so-called implicit one-class data. The user doesn't explicitly tell us, I like this movie a 5 or a 1, but rather, he will watch the movie or not watch the movie, and that's the only signal we get. And this is, of course, relevant across the many domains. It'll click or not click on a news story, or consume or not consume a game, and so forth. So we don't know how much this user 1 liked this movie, only that they watch it. And further, and more troubling maybe, is that user 2 here, we don't know if they didn't consume the movie because they didn't like it, maybe they didn't have time, maybe they weren't exposed to it. And so this sort of implicit one-class data, hence the name, is what we're forced to work with in many of these industry applications. So what does matrix factorization do? My thanks to the previous speaker for explaining this a little bit. But essentially, I take my full rank usage matrix and I decompose it into two other matrices, one skinny users matrix and one short items matrix. And essentially what I'm doing is finding a low rank approximation to this full rank usage matrix. Once I've done that, I can predict any entry, let's say this entry corresponding to a user U and an item I, by the inner product here of these 2 corresponding vectors in the decomposed representation. So I have an inner product, it spits out a number, and it tells me how much this user will like this item. So without going into too much detail, the actual finding of this decomposition can be formulated in many ways. One not mentioned by the previous speaker is this probabilistic formulation. And of course, we learn the parameters of these formulations from the data. In this work, we're going to consider matrix factorization as sort of a black box, so we won't go into these details further. Okay, so at query time, how do I serve recommendations to my user X? I have a representation for him, namely a vector in this low-dimensional space. I take the inner product with all the vectors representing the items in my catalog, and now I have a preference of this user over the entire catalog. I simply rank according to that number, right? And I recommend accordingly. A great advantage of this is that it embeds all my users and items into this low-rank space, right? So in addition to being able to compare users and items, right? This inner product is sort of a comparison of where they are in the space. I can also compare users and other users and items and other items, and this is in fact the intuition that powers many of these item-to-item type scenarios that we saw earlier. Similar items are also taken into account. So because of their semantic similarity, it's likely that Harry Potter 1 and Harry Potter 2 in my previous example would be mapped to a similar location in my latent space. And then a usage point from Harry Potter 1 and a usage point for Harry Potter 2 would, in fact, result in these 2 users being mapped to a similar place in the latent space. Again, we're only using the usage signals. So we're agnostic to what the actual domain that we're in. And so that's the advantages. What about the disadvantages? One big disadvantage is the so-called cold start problem, which was briefly mentioned before. Imagine a user who's never been to our system. How are we to know where they lie in this latent space and what to recommend them? Similarly, an item that's new to the catalog, we don't know who to recommend it to, really. So, in fact, in industry applications, many people still use content-based similarity to alleviate this problem, right? At least for those cold items. A lot of systems are hybrid. Another slightly more subtle problem is the more sparse our original matrix is, the more degradation we get in the quality of our performance. So now we get to our approach after much background. I don't have a clock up here, so let me know. Okay, I'll give you a little bit of background on this work. So essentially, these days there's a lot of like online retailers. They have a small store with a bunch of items, and they have users that buy stuff from this store, and then they end up with this regular data set of who bought what, and a returning user comes in and they want to offer this recommendation service. So Microsoft wants to team with these people to offer them a relatively free recommendation algorithm. The question is, beyond just providing them the box for the recommendation algorithm, can we make this recommendation algorithm better? And recall that these can be, retailers of apps or movies or whatever, and so a very domain-specific solution is not really an option for us here. We want something that's broadly applicable across many types of retail catalogs. And as you can tell by the title, we further improve that using the browsing log. So improving matrix factorization in this case, I just want to note, means improving a broad spectrum of recommendation applications because many of them apply this matrix factorization technology at least partially. Now, what are browsing logs? Browsing logs are pretty amazing. They're those logs of the user's search queries and those URLs that they surf to. And in fact, they describe the user's taste in a much more multifaceted and descriptive way than a user's interaction with any one retail catalog can achieve, right? And you can imagine that just having this information allows me to understand my user more. And you can also imagine that many users that are new to my system, certainly if they're online users of an online recommender system, have some other kind of online presence. And so this sort of information from the other part of their online helps to make my cold users into these semi-warm users, which I know a little something about their tastes, right? And in general, just densify my representation of my users. So a little bit about browsing logs. So I said there's search queries and URLs. And if we consider queries alone, they've been shown in many works, including this paper by Goel et al., to be able to predict many facets of the user. So if I'm wanting to predict age, sex, race, and so forth, demographic information, I can easily do so from a query, from the query log of the user. And URLs are even better than that, right? Just consider the situation where you have an ambiguous query, right? There's the information retrieval examples of Jaguar the car versus Jaguar the cat and so forth. Usually, that ambiguity is immediately resolved with the URL that you visit following your query, right? And and that's just an illustration of that the URLs have a much more rich semantic descriptive. So here we see many popular sites on the web, and we see the frequency of visits according to various demographic variables. So I don't know if you can see this, but for instance, sports sites are frequented much less by females than they are by males. And in fact, anywhere there's a gap, you can imagine that a visit to this site is very discriminative about this particular variable. And so the point being, there's huge semantic information, and certainly about users' tastes and preferences, especially when you're talking about things like the Windows Store, the Windows Phone Store, where you have apps, basically as many apps as there are tastes in the world. Okay, so I've hopefully convinced you that they're good. Now, how do we use them? We use this. Well, we actually offer several, but let's start with the first one, matrix expansion. So we take our original implicit one-class matrix of users versus catalog items, which has our dots for the usage points, and we simply concatenate it with another matrix which maps users to those browsing items, those URLs that they browse to, or those search queries. And then we proceed to perform matrix factorization after a few implementation details. Well, for one, we need to do some data cleansing. Some URLs are very popular. Imagine facebook.com or netflix.com. And they're not very informative about apps or games or so forth. Similarly, there's some that are visited by very few people, so we want to get rid of those. Another very helpful normalization is to take a long URL and normalize it to the host name. For example, cnn.com/politics/elections/blah, blah, blah becomes just cnn.com. And that helps us aggregate many usage points with similar semantics into a single token, right? Okay, so then we have this expanded matrix. We perform matrix factorization on it, and we end up with user vectors, item vectors for our retail catalog, and item vectors for our browsing items. Of course, we don't intend on recommending URLs or queries to our users, and so we discard these and then proceed with our recommendations as usual. How's the time? Okay. 9 minutes. Okay, so the second approach we have is called matrix imputation. And it relies on this so-called imputation function, which maps an item from our browsing items, in this case a URL, expedia.com, to an item or set of items from our retail catalog, in this case the Fly Delta app for Windows Phone. Using this imputation function, I can take my original usage matrix and impute these gray inferred points. So for example, I have a user who surfed to expedia.com. I insert a pseudo usage points for the Fly Delta app in this matrix. And so you can imagine I get a densified version of my original matrix. Okay, of course, this approach is only as good as the imputation function I choose. In the paper, we experimented with several such imputation functions, but I'm going to describe one to you, and it's called prob/all. And to understand this function, let's consider an entirely different matrix, where now the rows are indexed by the catalog items, and the browsing items index the columns. So each entry here is the number of users in our data that both installed, say, the app and browse to the URL. And we also consider the sum over the entries in each of the columns and normalize each entry by said sum. Our final imputation function is simply for each column / browsing item, we return the index of the maximum entry here in the corresponding column. So you can imagine that the normalization helps with those very popular URLs that are still in our data. And in fact, each column, the reason it's called probs is that each column now describes a conditional probability distribution over the item catalog, right? The retail item catalog, of course, conditioned on the browsing item. Okay, so we augment the matrix, and we perform matrix factorization. And then we have a user representation and an item representation as before. We actually found that it's helpful to discard the resulting user representation and construct a new user representation based on averaging the item vectors corresponding to the items in the user's basket. So that's just a detail. So does this stuff really work? We constructed some experiments in order to test the broad applicability of this approach. And in the retail data set, our interactions are clicks. With the item catalogs are clicks, and the goods in the catalog are physical goods. They're clothing item in a clothing store, be it online. In the apps catalog, well, the apps are virtual goods, right? They don't exist anywhere, and our interactions are downloads. And so hopefully this sort of has some variance, so we can say if it works on both, and it maybe has a broad applicability. Here we copy a table from the paper, which gives some statistics on these data sets. I will say, for those concerned about privacy, so the URL logs and query search logs were all given by users who provided consent. We didn't look at any user-level datum at any time, only aggregate levels. And they were all hashed, of course, for anonymity. There's no user labeled on anything. Okay, a little bit about how we judge the quality. It's a little bit differently from the previous talk. Essentially, we designate a bunch of users as test users. We retain n-1 of the items in their history, and the last item we retain as a test item. Come test time, we compute recommendations for each of these users, and we figure out where the test item ended up. Of course, we want it to be as close to the top as possible, and we compute the rank normalized by the length of the catalog, right? So we're able to compare different size catalogs. This sort of percentile rank is averaged over the entire set of test users, yielding us a quantity known as MPR. So because we're working with ranks, we want lower, right? Lower is better. Remember that when you see the graphs. Another metric we've defined sort of goes to the promise of recommendation systems. Recommendation systems hopefully expose the user to the long tail of the catalog, right? And a great way to get better accuracy in your recommendation system is pretty much to limit the number of items that you're going to recommend to the most popular items. Of course, this doesn't meet the promise. So this coverage metric essentially says how much of the item catalog is a candidate for recommendation. And the way we've constructed it is with higher coverage, we're considering more and more cold items. So low coverage means we're considering only the warmest items. And as we increase and cover the entire catalog, we're considering more and more cold items. Cold items, of course, are those items which have very few users. So how well did we do? Here we plot coverage against MPR. MPR is the goodness, you could think of it, of our recommendations. And we have two curves here. You're probably asking which one is the baseline. The slides are messed up, sorry. Okay, so our approach is this enhanced matrix factorization. It's the solid line. And the first thing you can see is it's lower, so we did better. So you can be, you don't have to worry about that. Another thing you can see is this so-called trade-off between coverage and accuracy, right? So as we increase the coverage, meaning we are including more and more cold items into our candidates, the recommendation problem becomes harder, and the MPR, as expected, grows. Actually, this effect is mitigated in the enhanced version, the solid line, and we can see that the slope is slightly less. Okay? So this is the matrix expansion. You're probably asking, what about matrix imputation? Comments on? 2 minutes. So the improvements achieved by matrix imputations are slightly more modest, but you must recall that in expansion, we also have more parameters, right? We learn more items and more, so we essentially have more items. So the matrix expansion is actually more computationally intensive to compute. So here, we do see an expansion, but there is a little bit of a computational efficiency versus accuracy trade-off here. Okay, the most interesting part in industrial applications is computing anecdotal examples. So let's see some of those. Here, we see someone who only surfed to Marriott.com, didn't have any previous interaction with the Windows Phone App Store, and these are the top 2 apps that they were recommended to him. So Marriott.com is, of course, a hotel chain. Fly Delta is an airline app, and OpenTable is a restaurant recommendation app. Here we see someone who surfed to Lego.com. He's recommended Hangman and Craft World, which are both games for the Windows Phone. Here we see someone who surfed to FoodNetwork.com. He's recommended Couch to 5K, which is an exercise app, and Weight Watchers, which is a diet app. Very interesting result. Here we see Hulu.com. We recommended AMC, a movie watching app, and Pizza Hut, which is a pizza delivery app. So in industry, we do this kind of subjective evaluation because we must, but it is subjective, so judge for yourself whether these are good or bad. Okay, so some discussion. In general, using URLs when you have them is better than using queries. We discussed this at the top. URLs are a more fine-grained semantic resolution. They give us simply more information. So that's interesting. URLs also capture short-term intent. We saw this in the example. When I'm traveling, I'm going to Marriott.com, and I also maybe want to use a flight app and maybe use a restaurant booking app. Our enhanced models are less sensitive to the inclusion of cold items, as we saw from the graphs, and that much is clear, but also consider that if we use only the warm items, we'll get an improvement. So the improvement is not solely due to the so-called warming up of our catalog. There's other factors, of course. So I hope I've convinced you that web browsing is extremely rich and powerful, and that it can be used to improve recommendation in a broad spectrum of applications. And here we present some ways to do that, and there may be others. But it certainly works. And with that, thank you very much.